Thank you for coming, and I'd like to thank the organizers of both the workshop and the program for the invitation. So this is a joint work with Leptos Kinetic from SPCI Paris Tech, and it's about following on the finances talk. It's about a lattice. So more specifically, oops, is there a way to figure no problems. All right. So more specifically, we're considering this chain of masses connected by nonlinear springs. So they're in rescaled version, the equation of motion is just like this. You already saw this in the finances talk. And here F is our interaction force, P is the potential. And we can write it down in terms of strain variables. And the equation become in this form. And what we're interested in is the interaction force that has this kind of interesting convex, concave, or hardening, softening structure. So actually, for I come from the world of materials. In materials, it's not very common in like regular materials. Not very common to see this type of interactions. Usually, you have softening, hardening instead, or just softening or just hardening. But in this case, this is actually motivated by biological material. So this is here. So this is the stress strain level in soft tissues, and so you can see. Thank you. You can see how it's softening and hardening actually after that it breaks. So soft tissues like tendons, ligaments, skin, things like that. These days they can mimic this type of behavior in even in like nuclear titanium mesh implants or metamaterials, like kind of needed metamaterials can mimic this type of biological behavior. So that's what motivates this assumption. And so we're interested in supersonic turbulent wave solutions propagated to velocity v. So we will have this form. And so as a result, if you plug it in, the quantum equations, you obtain the non-delay differential equation. And we're interested in solutions which join equilibrium states. And like I said, they have to be supersonic, so the velocity has to be above the sonic speed at each of the two equilibrium states. The two different types of solutions we are looking at are kinks. We call them super kinks because they're supersonic, so they could be going down or up like this. And we're also interested in solitary waves, which are just pulse-like solutions on generally non-zero background, non-zero background. So it could be tensile or compressive, I guess, bright or dark in Hannes's terminology. Both of these type of solutions have to satisfy the Rankin-Kurbanyan conditions, and also this equal area condition, which of course in the case of solitary, so W plus and W minus both equal to WB, these are trivially satisfied. But for kinks, these are actually important. And what this the second condition means, for example, is that the radial line which connects the two states must cut the equal areas from the force strain law. And physically, this means that there is no driving force on the kink. So there's no dissipation at the macro level. Unlike, for example, subsonic kinks, where there's definitely dissipation, or shocks. There's dissipation. So also these two conditions mean that for a kink you cannot prescribe W plus, W minus, and V independently. So if you, for example, prescribe the velocity, then W plus and W minus will satisfy some kinetic dependence on V from these two conditions. Now, this type of the kinks have been studied before in the leadership of Jos. Prove that they bifurcate exactly from this inflection point which connects the convex and concave parts of F. And then later we have Hermann and Jens and Mikhail Hermann, as you already heard from Hannes this morning, unfortunately just passed away. He had done a lot of important work, including on this supersonic kinks. They proved global existence results for the such solution. And yeah, I already said about zero driving force. And as far as exact terminal solutions, you can actually obtain them in some special cases. So, for example, in the Vainchtein case that I'll mention a bit later, Rabush and Drostinovsky obtained solutions both for kinks and derivatives. Okay, so all right, so we're interested in trying to understand how this kinks and so degrees are related, and one way to see that is to look at the quasicontinuum. I'm so happy I'm talking after Panis, so I don't have to like explain a lot of this stuff again. But this is the model that you have already seen in his talk. That's a regularized Wiesen's equation or Wiesen's equation, or whatever you call it. And basically, the way I like to derive it is just by approximating in the Fourier space the discrete Laplacian by this Floquet approximation. And then what you get is after a couple of integrations, you obtain a second order ordinary differential equation, which actually has the first integral. And you can check very quickly that you did recover the Vainchtein and the equal area conditions for this model. And then to see the emergence of super kinks and associated solid degrees, it suffices just to look at the phase plane for this problem. So this analysis of this problem. So if you let's say we kinks W plus and compute the corresponding super kink velocity, which can be obtained after sign from the area condition and from the area condition. So let's say it's positive, doesn't really matter. And then we also, like I said, then W minus is also fully determined. So then if I consider the phase plane at exactly at the velocity equal to the super kink velocity, this is what I see. There are two heteroclinic orbits, the red and the green. These are the two kinks, one going up, the other one going down. If I change the velocity just slightly below, so take it just below the super kink limit, the heteroclinic connection is destroyed, and instead we have a homoclinic orbit, which corresponds to the tensile circuit period, which originates at this left saddle point. If the velocity is above the super kink velocity, then we get another homoclinic orbit, which corresponds to compressive solid array. But interestingly, here emanates from that saddle point, whose value, the value of the WS, actually depends on the velocity. So basically, for given W, say W plus a hat, we have the solitary solutions. One with the background W plus, and the other with the background WSB. And so they're tensile or compressive, depending on which velocity, whether you're below or above the super kink limit. And as the kink velocity limit is approached, what is happening is already again in sequence with this diagram, is that this solitary become more broad and acquire the structure of kink-antikink model. So these are known in the literature as flat top symbols. Here, this diagram just shows you the in this picture, the tensile waves exist between the C plus velocity, which is just the sonic wave, sonic speed of W plus, and super kink limit. And the compressive waves exist between the kink limit and this C minus velocity, which is obtained by the tangent here, emanating from the W plus. Okay, so in this simple case of cubic interactions, you can actually obtain the solution. Well, in any case, we saw that let's just have a first order system. So in principle, we could integrate it for different potentials, but for cubic potentials, you can obtain nice explicit solutions. So here I'm taking cubic function. So this is basically, you think in terms of FPU model, this is the alpha beta FPU model. So you have both alpha and beta, but alpha happens to be negative. This is to ensure that we have this convex concave interaction. And so we are basically just restricting ourselves to the physical regime where f prime is positive. And then you can obtain solutions explicitly in this form. So for kink, you just have this Vainchtein profile. Everything is explicit. This is the velocity range. This is how W plus W minus depend on the superkink velocity. Here are some pictures to illustrate this. So W plus and W minus versus the superkink velocity, and this is how they look like. Basically by symmetry, it suffices to just consider the kinks that go down. Then for solitary waves, also things can be easily computed. So you obtain this type of solitary profiles, which tends to the background state, which I already mentioned. Depends, in one case it's just W plus, in the other case it depends on the velocity. So for tensile waves, for example, here you have this profiles of different velocities going from the sonic limit up to almost the superkink limit. And you can see that as we increase the velocity, unlike the usual FPU solitary waves, which just increase without bound in amplitude and become actually narrower usually, here they broaden and the amplitude saturates to approach the amplitude of the kink. And so this is for tensile waves, and for compressive solitary waves, as I already mentioned, the background changes with velocity, but in the end, the same thing happens. So you approach the kink-antikink bundle. Now, in this example, I chose W plus to be below this W star, which is the inflection point. If you choose W plus to be, so in this case, we saw tensile waves below the superkink limit and compressive waves above. But if you choose W plus to be above the inflection point, then it's the other way around. You first see compressive waves and then you see tensile waves. You can also plot both the amplitude and the so-called renormalized energy of the waves. Why renormalize is because the energy, is generally non-zero background, the energy is infinite, so you have to subtract the energy of the background. And so if you plot these things, here's the energy, here's the amplitude, you can see that there is a sort of graph here in the amplitude plot where exactly at the superkink limit, where you switch from tensile to compressive waves. And this is what happens with the energy, so you have this kind of asymptote exactly as the superkink limit. So superkinks, in other words, what I'm trying to say here, I guess, is that even though they look like different solutions, in fact, this solitary and kinks form a single family of solutions, with kinks just playing a kind of singular role in this family. So far I've just talked about the quasicontinuum model. So what happens in the discrete case? Well, for the discrete model, we can actually use the fact that this is a Terry base, so therefore there must be a periodic modular shift. So we assume here that also generated velocity is positive, and so we define this period of 1 over p, and then we have this relation. And so we can look for the solutions as fixed points of the corresponding nonlinear map. So basically, you prescribe the initial conditions, you resolve your governing equations, obtain the corresponding solution, and then shift the indices. And do this until iterate until you got the solution. So using the Gaussian equations. And we also have to prescribe a certain condition. And then after that is done, we obtain superkinks and tensile and compressive waves. So you can see, so this plots the circles are the discrete solutions. The solid lines are the solution to the Vainchtein model, and everything is plotted at the time t equal to 0. So you can see that actually because continuum model captures the solutions quite nicely. They're of course, they're not exactly the same, but there is, especially for the superkinks, the agreement is very good. And here we compare the corresponding energies of the solution. So this is again regularized energy, and oh sorry, this is the energy and this is the amplitude. And you can see that yeah, the red dots are the discrete, the black are the quasicontinuum. You can see that gradient is also quite good, especially near the sonic limit and the superkink. So the conclusion is the quasicontinuum model captures the single nature of the superkink limit quite well. The other thing we did is look at this stability, linear stability of the solutions. So to do that, we just linearized about the determined solution and computed numerically the Floquet multipliers of the corresponding monodromy matrix. And because it's a Hamiltonian problem, linear stability requires that all the Floquet multipliers must live on the unit circle. And this is not exactly the case because we believe some numerical artifacts of the fact that this is we are doing the calculation of the finite lattice, but there are some multipliers which go a little bit off this unit circle, but it's actually well known in this business that as you increase the size, it's also the case here, as you increase the size of the chain that you're computing things on, they approach, they come closer to the unit circle. So effectively, the solutions are stable. This was something similar has been observed, for example, in the work of Mari and Aubrey and many others. There's some permanent things. Just scholars. So we also checked using just direct numerical simulation, so we can just start with the corresponding turbulent wave and see how it propagates, and we saw robust propagation in the super kinks, because the super kinks with different velocities, and compressive and tensile surveys. This is just below the super kink limit, so you can see it's quite broad, and this is just about. In this case, sorry, in this case, W plus was above the versus the compressive. All right, Riemann smooth. Again, so happy I talked after Paris. So you know about Riemann type initial Riemann type simulations already, of course. So here we just prescribed some left and right strains in this kind of piecewise constant fashion, and zero velocity, strain velocities. And what you see is that after a while, you see formation of a super kink, which is kind of hard to see here, but if you zoom in, you can see it quite nicely. It is followed by a weak dispersive shock wave. Here it is. And then, so that both of these things propagate actually to the left. And to the right, you see another quite strong dispersive shock wave which propagates. So here I just wrote some velocities here. So you can see that the super kink moves its velocity approximately 572. It's followed by a dispersive minus 572. This is the velocity of the dispersive shock wave which follows it, and the other dispersive shock wave moves to the right of this whole thing. Okay. So what this illustrates, and there were other solutions like this. This illustrates that super kink quite robustly formed from like just generic Riemann initial data, along with dispersive shock waves, which I guess is of interest to many people in this room. All right. So another thing we did, and I just want to briefly mention this in the interest of time, is the case of trilinear interactions. So again, this choice was motivated in part by biological applications. So in tendons, which is something that every age we discovered, we need to know about tendons, which we didn't think before, and ligaments and things like this. It turns out that when I measure stress strain curve in tendons, they are very soft here, and then they have actually this kind of linear regime, and then they become kind of so there's a soft type of stress strain laws that they see in this type of material. And so that's what we kind of assume here. Oh, so this is this section soft compared to the green. So the blue regime is soft compared to the green regime. So beta is always greater than 1. And then there's another alpha regime, which is actually we allow it to be all the way from 0 to beta. So so in particular, a nice symmetric case when alpha is equal to 1 has already been studied. Oh, and also when this beta is infinity and this delta parameter, which measures the width of the of the green regime, is 0. This case was studied by Garbush and Justinovsky in the earlier works, and then there you can just use Fourier transform to nicely obtain all the relevant solutions. Here, I mean, we've done the work we've done includes all of those cases, but just again, in the interest of time, I'm only going to consider the case when alpha is equal to 0, which is a particular interest in this, turns out. So when the alpha regime, the red regime, is inelastic. So this is what it looks like. And in this case, like in other cases, we can obtain again quasicontinuum solutions and discrete solutions and compare them. And you can, but what's interesting in this case, you can actually obtain some of the discrete solutions analytically. This is what we thought equal to 0. We can compute solution, and this is what it looks like at t equal to 0. So this is for the range of velocities between 0 and some upper limit. As it approaches the sonic limit, which in this case, because the regime is inelastic, the sound speed is actually 0. So it's kind of like the granular materials without precompression that Panas was talking about this morning. So as it approaches 0 velocity, this solution actually becomes like this. It becomes a W plus everywhere except this one point where it becomes WC plus delta over 2, which is exactly this value over here. But the quasicontinuum model doesn't do quite exactly the same. It actually, oh yeah, and the important thing here is that these solutions are all, if you remove the background, they're compact. So the compact structures on top of there's the quasicontinuum model. In the limit, we get this kind of exponential decay. So it's not exactly compact. So that this is where quasicontinuum doesn't quite capture the whole thing. Okay, and this left plot shows you the so this is close to that the 0 velocity limit that I was just talking about, and this shows you for the entire velocity range. Again, you can see this kind of broadening of the solutions as they reach the kink-antikink limit. And on the right, you see the amplitude of the solutions and the renormalized energy. Now, this black is the quasicontinuum. The red, the computed, numerically computed discrete values, and the dashed green. I don't know if you can tell. Yeah, there is a dashed green here. That's the exact solution that we. Okay, so to me, the most interesting thing about this problem is this slide here. So we did some simulations with Zoom data, and what we saw is quite different from what I showed you earlier with dispersive shock waves and stuff. So here, instead of a dispersive shock wave, well, you do see, first of all, let me say, you do see a formation of super kink, right, with the Zoom simulation. But instead of the dispersive shock wave, what you see instead is you see a formation of a shock which connects the constant state to this kind of periodic solitary wave train. So this is maybe it's a little bit hard to see in terms of like in this. So here's a plot strain versus n, the site number. So instead, let's plot it in versus time, and you can see the periodic structure of the train quite nicely. And I don't know if you can tell it here, but there is a. This is the space-time diagram, which you can also see this. So so there's super kink which travels with this velocity 1.52, and then there's dispersive shock connects train of solid waves to the constant state, and then behind it. So Yeah, so with that, let me just summarize. Oh, and by the way, I should mention maybe before, yes, so this is not just an artifact of this kind of piecewise linear model. I did recently some simulations for the case where you have sort of Vainchtein type, the FW is Vainchtein type interaction, and you also see the same effect. So this is has to do with this, inelastic behavior, and not just some kind of piecewise linear effect or something. Okay, so conclusion. So we looked at the FU problem with hardening-softening interactions, which in addition to this solitary reconciled compressive supports kinks, super kinks, which are dissipation-free, and we saw that as the super kink clinic is approached, the solitary require this kink-antikink bottle structure. Of course, this type of solutions have been seen before in other contexts, for example, in probably in MPD, but also in the recent work of Rosenau, collaborators, Gardner equation, things like that. As far as I know, they have not been seen before until recently in the context of FBU. Turns out that this quasicontinuum model actually does a pretty good job of capturing the solutions, which in this case we most obtain using a linear approach. And then we also did a lot of Riemann type initial data simulations which show formation of propagation of super kinks, and I haven't shown you all the results of the count, but you also see formation of solitary waves and things like this as well. And if you would like to know more, especially on this triangle, which I basically just only talked a little bit about, there's this preprint on active papers submitted, and then there's also published work. Thank you very much for your attention.
Kinks are typically related to under-suppressed shock.
Yes, but these are not under.
These are not.
These are Supersonic.
It's a Supersonic. Okay.
Yeah. In this discrete model, you can also have subsonic kinks, but those will have oscillation.
Yeah.
Yeah, because they don't have participation.
I just have a more practical question. Where you mentioned this stress strain relation for ligaments and tendons.
Yeah.
I mean, it's not really so much related to stuff, but like say if you stretch, like do you want to go into the, into the alpha, into the beta regime? Or, yeah.
Sorry.
So let's say, I'm sorry, so when you do a workout before you stretch, right? So you think you're supposed to go into the beta
suppose
regime?
so. Yeah, I don't know exactly, but I suppose that's the routine. But what you don't want to do is get here. Right?
No. Okay.